me do that.
Okay. Okay. Can you see my screen?
Yep.
Yes.
Okay, thank you very much. Just before starting, I would like to thank for organizing this lecture and invitation. Especially thank Professor Nakamura and my dear friends Haruki. And let me start this lecture. I hope that this talk will be useful and interesting for you. The talk about application of spectral methods in numerical solution of differential equations. And let me start with that. Okay, I will start with an introduction about the differential equation and its characteristics, and then I will talk something about the finite difference method to solving numerically differential equations, and then we'll talk about spectral methods, foundation of it, and comparison it with finite difference method and implementation and its application in computation of quasi-harmonic modes. There are too many differences. There are too many references about the spectral method in the web, and among of them, I choose these two references. Those I think are the best and are the most complete references for the spectral methods. The first one is a book by Boyd titled Chebyshev and Fourier Spectral Methods that is available freely in the homepage of the Boyd that its URL is shown. And the second one is a review paper published in Living Review in Relativity, and its archive number is shown. And as well as them, there is a lecture note by me based on the previous workshop on the spectral method and Ferdowsi University of Mashhad 2 years ago. And I will update this notebook after this talk, and it could be shared with you if you are interested. And let me start with an introduction about the differential equations, definition of that, and the characteristics of differential equations and numerical solution of them. Okay, as you know, almost all of physical concepts in physics are described by differential equations. Maybe the simplest example is the Newton's second law of motion that says that the force on the acts on the body is proportional to second derivatives of its position with respect to time. And generally, if you consider independent variable such as x and a dependent variable y as a function of x, we can define a differential equation as a function or a mathematical equation between the dependent variable and its derivative, as you see in the I don't know you can see my cursor or no. This function or this mathematical equation between dependent variable and its derivatives, so-called differential equation. That the ynx shows the nth derivative of y with respect to x. If you generalize this one, and you have a set of independent variables labeled by m, and the dependent variable as a function of the set of independent variables, and the yn shows the partial differential from these independent variables. And this one is so-called ordinary differential equation, or ODE, and this one is partial differential equation, or PDE. and capital M is the number of the independent variables. So let me discuss about some characteristics of the differential equations. The first one is linearity. If you can write down a differential equation as here, and the coefficient as a function of independent variables times to some times to the dependent variable or its derivatives equals to a function of independent variables. If the dependent function or its derivatives appear with powers higher than 1, or appear cross terms, I mean, for example, y times y prime. This PDE or EDE is nonlinear, and except that it is linear. Notice that the an as a function of x, or g in the right hand side of the equation as a function of x, could be nonlinear function of x, but the dependent variable should be appear only with power 1, not higher. And there is a classification about the second order differential equations as elliptic, parabolic, hyperbolic, and diffusion function. The elliptic form is here, such as the Poisson or Laplace equation, and the parabolic one, this relates the first derivative with respect to time to the second derivative with respect to x. And the hyperbolic is such as the wave equation, and the diffusion is this form where you set c as equal to 0. This reduces to the parabolic one. And the higher order of the derivative appears in the differential equation known as order of the PDE, and the number of the independent variables known as dimension of the differential equation. Usually time is not to account in counting dimension, and only spatial directions take to account. And in some of physical problems maybe exist several differential equations coupled to each other and several dependent variables, and we can have a set of differential equations and solve together to find dependent variables. Okay, and the last characteristics I want to mention is bound condition that's specify the unique solution of the differential equation satisfies this condition. About the boundary of the interval, the independent variable defined on that. And there is at least these three famous form of the differential equation: Cauchy, Dirichlet, and Newman. And based on the physics of the problem, we can use one of these. Also, after that, it is useful if we mention about numerical solution and answer this question: what we do mean when we say about the solution of the differential equation. The solution of the differential equation is finding dependent variables as a function of independent variables, and it could be analytic or numeric based on the problem and based on the form of the differential equation and based on its complexity. For analytic solution, it is doable with direct analytical integration by hand or by software such as Mathematica by DSAL command. Uh, but in numeric solution, we have to discrete the domain of the independent variable uh, into the grid points and find the value of the dependent variable at each grid point. This means the solution or numerical solution of the differential equation. Okay, let me start with solution of the differential equation with finite difference method. The finite difference method based on the Taylor expansion of the dependent variable, as you see here. The value of the y at I plus 1th grid points is equal to the value of the dependent variable at ith point plus delta x and the first derivative at ith point. Delta x is the difference between two grid points that in finite difference method, the difference between them are the same. So you can find the first derivative value at ith point based on the value of the y at ith point and the next point over to the delta x, that is error order. And this is so-called the forward approximation or forward finite difference approximation to find the y prime. If you transform the I into I minus 1, you can construct the backward approximation that the value of the derivative at ith point is dependent on the value of the function at ith point and the previous point. The error order in both of them, forward and backward, is delta x. That is proportional to 1 over n if n is the number of grid points. And if you truncate some other sentences here, you can find the first derivative based on the value of the y at the next point and at the previous point over to 2 delta x, and the error order decreases delta x squared. And also in this order, you can find the second derivative values at this point with the same error order. So let me check the finite difference approximation convergence and error. If you consider a function as such as sine of 2x, and plot is at as the dashed line, and try to estimate it, but Taylor expansion of finite difference series for different number of n, capital N. Capital N means the number of grid points, and small n is the number of order truncated from the expansion. For example, or if you fix the order of expansion as 3, and you try different values of the grid points, you can find the estimation of the sine of 2x. And as you see here, by increasing the number of grid points, you can find the smaller error, and your estimation will be more good. And this decays as 1 over n cube. And also see the second row. If we fix the capital N, I mean number of grid points, to 9, and change the order of the expansion, and you see that by increasing order of expansion, this is the maximum difference between the exact sine of 2x minus the finite difference series decays to, for example, 10 to power 11 minus 11, and decays as 1 over 9 powers to n. We can summarize that the error in the finite difference method decays as 1 over n powers to n. I mentioned again that capital N is the number of grid points and the small n is the order of the Taylor expansion. For implementation in Mathematica using finite difference method, it is sufficient you use the ndissolve command that is use the finite difference method and finite elements method and switch between them adaptively and based on the form of the differential equation. For example, it is shown here the solution of this differential equation by the boundary condition y at the 0 equals to 1. And this is the solution of the this differential equation by finite difference method. Okay, let me dive to the spectral method by saying about its foundation and about the Chebyshev polynomial boundary condition, and finally comparison between this and the finite difference method. In the spectral method, we change or VQ into the differential equation. We see the differential equation as an operative equation and consider an operation such as L act on a y that is unknown function and give us the source as a function of x. X is the independent variable here. In this method, we estimate the unknown function as a power series based on some polynomials and insert this into the differential equation. This basis of the expansion should be complete and should be easy to compute. Should be complete because we can because we like to write down any function based on these polynomials, and easy to compute to avoid being more complex the differential equation. And inserting this expansion into this operative form of differential equation and demanding that this differential equation should be satisfied at each grid point, we can see that acting L on the spectral series of unknown function at each grid points, I mean xi, gives us the source value at that grid point. Okay, let's be more clear. There is two approaches to solve this form of differential equation. In the approach one, you act the operator on this spectral series, and you give the source. This creates the domain of independent variable as here by a consistent generator that I mentioned later about that. And for simplicity, consider the operator is the first derivative with respect to x. And demanding that this form of the differential equation satisfy at each grid point, we will have this system of the equations. This is the expansion of this summation after acting this operator, that is first derivative of with respect to x. And at x0, that is the first point of grid points, equals to s at x0. and so on for other field points. This is n equations and unknown systems. The unknowns are the coefficient of the series a0, a1 to an minus 1. And these are the n equations. And we can solve this system and find the coefficients and insert here. Sorry, insert here and find the form of the x. This is the so-called known as the coefficient space, and we see the coefficient as unknowns in our systems. The second approach that is usually used more than the first approach, we estimate the unknown function as here. Instead of the unknown coefficient series ai, we use the value of y at xj and replace the polynomial with a function cj that I say about that more later. Yxj based on the polynomial you used for the expansion of your unknown function defined as this. Summation on ai phi xj, and the cj is so-called cardinal function, is defined based on the polynomial you used in the way that the cj at xi to be equal to delta ij, and inserting this form of the unknown function into the operative differential equation, operative form of the differential equation, we again have a n equation and unknown system, but here the unknowns are the values of the y at x at each field points, not the coefficient series. This approach is the work in collocation space. Okay. Before talking about the implementation of spectral method, it is useful to say something about the Chebyshev polynomials. The polynomial you select to construct the spectral series of unknown function should be easy to compute and should be complete and should be rapid convergence. Among too many polynomials, you can select them. The Fourier and Chebyshev usually are used. Usually for the problems that the unknown function satisfy a periodic boundary condition, usually you use the Fourier series for unknown function, and for other problems, at most use the Chebyshev polynomials. The Chebyshev polynomials are the solution of the Sturm-Liouville differential equation in this form, with p, q, omega, and lambda to be set as here. And by definition, the zeros form the Chebyshev polynomial is 1 and t1 equal to x, and this recurrence relation to find the tn. And some characteristics of the Chebyshev polynomials listed here for even values of n. Tn is even function of x, and also for odd values. And the highest power of x in Tn x is n, and Tn at plus minus 1 is equal to plus minus 1 power to n, and Tn has n zeros in the interval between -1 to 1, and this is the completeness relation for the first type of Chebyshev polynomials. Also, by changing a variable x transform to the cosine of theta, we have the Tn of cosine of theta is cosine of n theta. Based on this definition, you can discrete the independent variable domain with a cosine generator of cosine of pi I over n minus 1. That is known as Gauss-Lobato generator. And it is clear that the geared points are not equidistant in this method. And be careful about the interval generated by this generator, that is cosine generated from -1 to 1, and this interval have to map to the domain of interest in your problem by a relevant transformation. For example, if you if you work in from 0 to 1, you have to map the -1 to 1 to 0 to 1. And in collocation space, based on Chebyshev polynomials, the cardinal function, remember this form, the cardinal function is defined as this. Derivation of this and calculating this derivative is mentioned in the first reference I mentioned. I said at the start of the talk. I mean the book by Boyd. And the cardinal function is this, and its first derivative we show with this symbol is a n cross n square matrix, and their elements is shown here. And the very important benefit of the Chebyshev polynomial is here, that the cost order, the cost derivative defined as the first derivative to power k. This is very important to make matrix form of the differential equation, and it is very easy to use any order of a differential equation easily. Okay, let me go ahead. And for example, if you have this form of a given differential equation, the operative form of that is the first derivative matrix plus 2, sorry, the second derivative matrix plus 2 the first one, and plus 2 the n cross n square identity matrix acts on a column matrix of yx equals to column matrix of sx. So the differential equation converts to a matrix equation and could be solved more easily. The important point is that applying boundary condition in this method. Sorry. To apply the boundary condition in the collocation space and collocation method of the spectral method, we replace the first row and the last row of the operation matrix form by this form. The first element is 1 and the others are 0, and here the elements except the last one is 0 and the last one is 1. If you times this row in this column, all of them vanishes and remain y at x0 equals to s at x0. If the boundary condition defines as y at 1, it means that y at x equals to 1. No y at x and index 1. Y at x equals to 1 that is y at x0 equals to y1. So it is sufficient that replace sx0 by y1 and the s at xn minus 1 but y minus 1. And by this changing and replacing, the boundary condition will be applied in this method. And this is sufficient that you solve this matrix equation and find the y at x1 to y at xn minus 2, and you have the solution of this differential equation. It is useful if we compare this method with finite difference method qualitatively and quantitatively. In qualitative view, in the finite difference, if you remember, if you remember, for example, for second order, the value of the first derivative at each point depends on the value of the function at the next and previous point. It is shown schematically here. The value of the derivative in this at this point depends on this the value of the function at this and this point. So only 2 points contribute to computing the derivative value at this point. But in a spectral method, there is one high order polynomial for whole of domain, and to compute the derivative value at each point, all of points contribute, and it is shown that the spectral method could be more accurate than finite difference qualitatively. Let me more precise and quantitative comparison between them. I solved a differential equation, a given differential equation, for example, by the third order finite difference, fifth order, seventh order, and by a spectral method. For different value of the number of grid points. As you see here, the spectral method decay error of the spectral method decays as exponential of -n, and only for 30 points of grid points, 30 number of grid points, the error is 10 power to -15. Be more precise, for the 30 points, the third order is the error approximately equal to 10 to power -5, and the fifth order -8, seventh order -11, and the spectral method -14. And notice that using the seventh order of the finite difference is very so time consuming and very difficult to implementing in writing the code. And while the spectral method is very faster than the finite difference and easy to write down as the code, as you see later. Okay, after this introduction and introducing the foundation of the spectral method, it is useful to see some simple example, very simple example in different cases to implementation spectral method. I will show simple examples in one-dimensional, multi-dimensional, time-dependent, and nonlinear cases.
Excuse me, can I make
yeah.
a naive question?
Yeah,
So
yeah.
is there any weak point in the spectral method? So according to your presentation, it sounds like it's always advantageous to use spectral method compared to the finite difference method. But is it always better to use spectral method?
Yeah, for some differential equation that is simple, or the accuracy is not essential for us, uh, mm, it is better to use the finite difference method by ndsolve command of Mathematica. That is easy to find the proper results. And writing down the writing down the spectral series and discreting and making metrics is itself more time consuming. It is a trade-off between the time and simplicity of the differential equation.
What about the calculation? What about the calculation cost?
Yes, the calculation cost of the in the spectral method is very low, and the time consuming for a spectral method is very less than the finite difference for the equal error requested in these two methods.
All right,
Yeah.
thank you very much.
I also think it's not time efficient when the boundary conditions are complicated, but that is not the case in usual holography programs.
What do you mean?
Yeah.
Are you saying that it is difficult to impose complicated boundary condition when you are using spectral method?
Yes, the expression of boundary condition are very complicated. I think the spectral method is not time efficient.
Yeah,
Really?
that's right. Yeah. Usually in the problem it's time dependent. Well, let me mention later. For example, in one-dimensional second order differential equation, as here with this boundary condition, the operator form is the second derivative minus 4 times the first derivative plus 4 times the identity matrix, and the source function is exponential of x minus 2. Okay, you can find the numerical solution of this equation by spectral method by writing this some lines coding. Here you discrete the independent variable domain by Gauss-Lobato generator, and here define the first derivative as I mentioned some slide ago, and the second derivative defined as first derivative to power 2, and make the equation operative form as the second derivative minus 4 times first derivative plus 4 times identity matrix, and define the source column matrix, and replace the first row and the last row by the proper values 1 and 0 to apply the boundary condition. No, using the linear solve of the linear solve command of the Mathematica, you can find the value of y at each grid point as a solution of this differential equation. And this is the results. The dashed line is the analytic solution of the differential equation, and various color of points shown the spectral method corresponds to various number of grid points. It show the convergence of the solution after, as you see, after approximately 18 number of grid points, we reached the 10 to power minus 15 in accuracy. And this is shows the stability of the solution after approximately 20 grid points. Okay, for multidimensional, I say briefly, if the dependent variable or unknown function independent variable labeled x1 and x2, the spectral series write down as here, and consider this famous two-dimensional differential equation, this Poisson equation, based on the collocation space and cardinal function. We can approximate the f(x) and y as this summation fij times two cardinal second derivative cardinal function with respect to x, that is correspond to this term, the second derivative with respect to x, times the cardinal function as a function of y plus the vice versa. And let me sign this parentheses as LKILJ times to Fij and summation and I and j equals to SKL. The Fij is the value of f at each x and each y in the grid points. The grid points is here is the two-dimensional and discrete in both of x and y direction. And this is the two-dimensional matrix of the unknown function. The f11 is the value of f at x0 and y0. This is the value of f at x0 and y1 and so on. It is better that convert it to a column matrix. The first row is here, and then the second row, and then other up to reach the last. And the operation matrix form is here, where L is defined as the cardinal function based on the Chebyshev polynomials. And finally, you have a L matrix with this rank, and act on a column of f, that is unknown function, equals to the column of S. And as an example, consider this equation with these boundary conditions. And this is the form of implementation of the mathematical, and you can see the results. This is the analytical solution of this equation, and this is the spectral solution with NaX and Na equals to 3 grid points, and this is for 9, this is for 13. As you see, by increasing the number of grid points, the spectral solution tends to the analytical one, and the number of NaX and Ny could be inequal. Okay, let me say something briefly about time-dependent equations. The first derivative with respect to time of y as a function of x and t is equal to some sentences that makes by acting this operator on y, and we can write down the y is equal to exponential of L delta t in this form, and the infinitesimal form of this, and we can write the value of y at n plus 1 time step as acting this matrix on the value of y at the previous time step. And let me skip from more explanation about solution, and you can find more clear explanation from the references I mentioned at the first. And other cases is non-linear. In non-linear cases, we combine the spectral method with Newton-Raphson iteration. As you know, by Newton-Raphson iteration, we can find the root of nonlinear function or nonlinear function as this form, and iterate this. And we can apply for this differential equation, for example, yn equals to yn minus 1 and minus f over a Jacobian. And the column matrix of n is equal to the matrix of the second derivative based on Chebyshev polynomial act on y minus y squared minus the identity column matrix. And the Jacobian is a derivative of that with respect to y, and can write them as this matrix form, and find x as these terms, f over Jacobian. And by finding these terms, we can find the y at yn equals to yn minus 1 minus x. And for it, by iteration, by iterate this task, we can find the solution. For this equation, for example, we find the analytic solution as solid black line, and other are spectral method results for different values of iteration. This calculation is done for 30 number of grid points, and as you see here, after 4 iteration in Newton-Raphson iteration, we collapse to the proper result with difference in order to 10 power to minus 11. Okay. It is useful. It would maybe useful if we mention something about the application of the spectral method to find quasi-normal modes. The quasi-normal mode, as you know, is the solution of linearized fluctuation equation of a black hole that describes distinct perturbation and holographically is dual to a small deviation from the thermodynamic equilibrium. And based on the holography, the quasi-normal modes are equivalent to poles of the correlation function or retarded Green function in the field theory. And the quasi-normal frequencies would be complex, that its real part is the energy of the fluctuation and the imaginary part is the damping rate. And to compute the quasi-normal frequencies, usually use the shooting method and relaxation method to find to solve the fluctuation equation numerically and find the frequencies and search the frequencies that at which frequency the fluctuation equation should be satisfies the boundary condition. So the frequencies name as quasi-normal frequencies or quasi-normal modes. This is the usual method to find the quasi-normal modes in in too many studies. But the shooting method and the relaxation method should be time-consuming and low accurate if your fluctuation equation be complex. Recently, the spectral method is used to find quasi-normal modes, and I forgot that mention spectral method is widely used in other topics in today's science, not only for general relativity or particle physics. Fluid dynamics, electricity engineering, mechanical engineering, metallurgy, and geophysics, and others enjoy spectral methods. And recently, there are too many papers. There are many papers that use the spectral method to find quasi-normal modes in different problems. It converts some hours or some days in some problems into some seconds or some minutes to find the quasi-normal modes in more accuracy and more in the number of the quasi-normal frequencies, as you see later. In this method, the fluctuation equation converts to an eigenvalue equation, and the eigenvalues of this new form of equation are the quasi-normal modes, and the eigenfunction are the fluctuation equations. In this view, you convert the differential equation as this form, that is M is a matrix operator acts on the unknown function, could be written down as this form based on the rank of the power of omega at a given fluctuation equation. Omega means the quasi-normal frequencies, and writing down this form, we can find the eigenvalues as quasi-normal frequencies in this form. If we can if we say more clear, we can set these 10 steps to find a spectral method to find the quasi-normal mode with the spectral methods. The first step is changing the coordinates to be finite domain of the independent variables. Then write down the fluctuation equation in new coordinates and find the behavior of fluctuation equation near boundary and near horizon. I mean the near of two ends of the interval. And based on the behavior of the fluctuation equation, redefine the fluctuation function to absorb the singularities into the new defined functions, and make the operator M as a matrix based on Chebyshev spectral cardinal function that is mentioned in previous slides. And then decouple the omega dependent terms and make the eigenvalue equations and eigenvalue form in the face of the fluctuation equation. Then make grid points by Gauss-Lobato generator, and solve the eigenvalue form of the fluctuation equation by eigenvalue command in Mathematica, and check the eigenfunction corresponds to quasi-normal modes you found if they satisfy the boundary condition or no. And increase the grid size and repeat the step 8 and 9 to check the convergence of the quasi-normal mode you found. There is
Excuse me?
Yeah.
Can I ask about the step 6 of the previous slide? So you said that you decouple the omega dependent terms, but in the previous slide, you show the equation which contains higher powers of omega. So what do you exactly mean by decoupling the omega?
I mean that make the fluctuation equation in this form. Yeah. When you construct this form, you can say you can write that M0 act on phi, for example, equals to minus omega M1 acts to phi. Yeah. then the omega is the eigenvalue and phi is the eigenfunction. Decoupling means, yeah. Okay, there is a
sorry. So could, so when the equation motion contains higher powers of omega, how do you get omega by using the eigenvalue function of the mathematical? Could you explain that part again?
You mean including omega square?
Omega square or up to omega p or something?
Yeah, good question. In this form, you have to, for example, if you contain the omega squared in your fluctuation equation, you have to twice the grid size. For example, if your grid size has n points, you have to convert to 2n points, and find the and find the eigenvalue in this manner. If you use this package, this package does these processes automatically, and it is sufficient to download that from this URL and install that in the proper directory in your computer and load that, and use the commands to find the quasi-normal frequencies, and it does all of the 10 steps automatically based on your shape, based on your fluctuation equation shape. And there are some commands based on this package, and there is a tutorial that I mentioned here, and this package is adjusted by Aron Jansen, that is cited below of this slide. Okay, as an example, after the installation, the QNM spectral package, it is sufficient to go to the document center of the Mathematica and search the QNM spectral, and you could see this tutorial, and there is a simple example from the for the computing the quasi-normal frequencies. And as an example, I reproduce the quasi-normal frequencies of this paper, where they use the shooting method, and using the Frobenius series and truncated 215 terms of Frobenius series, and spend some hours time to find these 10 quasi-normal modes in mass scales. But using the spectral method by only 80 points in less than 1 minute, I could find these 13 quasi-normal frequencies, 3 more than this, and with higher accuracy than shooting method. The very less time than this, and the time consuming with this configuration is about 40 seconds or 55 seconds, 1 minute. And also some other results between results of this study, and reproduces by relaxation method by some hours length, find these values, and spectral method, this configuration in 30 to 40 minutes, I could extract the results with more accuracy. Okay, I can summarize the talk. That is, the spectral method is fast and accurate method, and Chebyshev polynomial is usually used because of being easy to compute and rapid convergence in the spectral series, and spectral methods also help to compute quadratic modes. And any eigenvalue equation could be used spectral. And I think that I hope that this talk was interesting and helpful for you. And thank you so much for your attention.
Thank you, Mahdi. And can I have some questions?
Yeah.
Do you think the reason why the spectral method has not been used for the QNM problem in the ADS-CFT so far?
It is used. It is used in some problems, especially for problems about ADS numerics. I mean the problems in ADS-CFT about the evolution of the ADS bulk, and when they want to use the spectral when they want to compute the quasi-normal mode, use the spectral method.
I just mean, as far as I know, the Schroding method and the realization method are used more frequently. You said the spectral method is more cost-effective than the finite difference method. So in this context, some previous researchers who studied the QNMs in, for example, in the D3, D7 model, should solve the eigenvalue problem with this method. But most of the researchers didn't do so.
Yeah, good question. I think that as I remember, as I know, the spectral method entered the high energy physics with studying the non-equilibrium systems holographically. If you see the famous paper by Chesler and Jaffe about this ADS numerics in general relativity, that they study and try to solve the time-dependent Einstein's equation as the dual of the evolution of out of equilibrium system in field theory. They use the spectral method to solve the time-dependent Einstein equations, and as I saw and as I know and searched, the persons that the persons those are familiar with this method in other tasks use spectral methods to find consequent modes, and maybe others are not familiar with this method, and I think.
Okay, thank you.
Yeah.
Okay, so does anyone have any other questions?
So I have one question. Yeah, thank you very much for a nice lecture on spectral method. And I wonder how to implement the so-called ingoing wave boundary condition in the language of spectral method.
What do you mean from ingoing boundary condition?
Well, it's a boundary condition when we study the quasi-normal mode.
Yeah. The Chebyshev polynomials is automatically satisfies that boundary condition. It is another points the Chebyshev polynomial.
Yeah, that's the point. And do you have any more explanation why the Chebyshev polynomial satisfies ingoing wave boundary conditions?
Yeah. I think that yeah, I think that this figure could be useful for your questions, and when all of them at the point x equal to 1 is 1, and it seems that it is very important to that, and other condition we use in ingoing boundary condition, that is the fluctuation equation at the boundary could be 0, if I say correctly,
Yes. Right.
and yeah, the even number of this sorry, the odd number of this sorry, this is between -1 to 1, and it should be mapped to 0 to 1, and the spectral method based on Chebyshev polynomial is easy to apply any boundary conditions only by changing the first and the last row in the matrix. Yeah, here. And but this changing, you can apply any boundary condition. And the package I mentioned used and applied this automatically for boundary condition. This form is only for collocation space and collocation method of spectral.
Okay. Thank you very much.
Does anyone have any other questions? Okay, so Mahdi, thank you for your presentation today.
Thank you for you and for your invitation in organizing this lecture.
Okay.
Okay. Now
So,
I will stop the recording.
Okay.